Today's title is very long, the central limit theorem, law of large numbers. And that theorem and laws seem to cringe people, but there's really nothing to it. There's no theorem and there's no law that we're going to talk about. We're going to talk about a phenomena, a concept, a principle. And these two are two aspects of the same phenomena. And once we see what this phenomena is, we'll have no trouble understanding it. The hardest part will remembering which is which. Which part of it is called the law and which part of it is called the theorem. And I'll show you how to remember those a little bit later. So let's get to it. Population. Let's say we have a population looking like this. Uniform, a distribution which is uniform between 1 and 5. Here's 1, 2, 3, 4, 5. Uniform between 1 and 5. Well, what is that? Well, I can do that by taking a dial, a dial with an arrow on it, and marking this off as 1, 2, 3, 4, and 5. So I can go somewhere between 1, 2, 3, 4, somewhere between 1 and 5. I can uniformly, when I spin the dial, I can read it as precisely as you like, and I can say 1.321 or whatever. So I get some number between 1 and 5, and I'm equally likely to get any number on the dial because of the way this dial is spun. It's laying flat on the table. You spin it, and it can be any number between 1, which is here, and 5, which is also there. So you're really not going to be able to get the exact 1 or the exact 5, but anywhere between 1 and 5. Okay? So that's what's going on. Now what happens, I want you to do, is each of you spin that dial. You get a number between 1 and 5. Now if you each came and we plotted it, that is, we took a penny and we put a penny over your number and we filled it in, what would happen is that the distribution would look like that, and the plot of all the data would look like that. Lots and lots and lots of data. All the data, plot them, and it looks like that. And everybody's happy. That's the distribution of the data. No problem. Now, what I'd like you to do is instead of coming to me with one number each, I want you to pair off. Pair off. Every two people come together, and before you give me your number, you add them up and divide by 2. That'll give me the average. X bar, the average, we'll talk about that. We call X bar the average. So give me the average of your two numbers. So each of you has a number that comes from this distribution, and you've taken your numbers, you add them up, you divide by 2, and you give me that average. And now I plot those. What it looks like, the plot will look like this. Now you say, oh, that can't possibly be. Well, yes, it is. What's happening is that there's really no chance of two of you getting 1s or numbers real close to 1. There's really no chance of you getting numbers real close to 5. One of you might get a small number, one might get a big number. If you average up small number and big number, you get a number near 3. So the numbers near 3 are going to come up much more often than the numbers near 1 or near 5. In fact, the distribution will look exactly like that. So with an awful lot of data, when I plot them, put pennies on, I will get very little on the ends, a lot in the middle. It'll be a triangular distribution. That's what will happen with just 2 observations in your average. Now, instead of 2 of you coming together, I want 5 of you to get together. 5s. Come to me in 5s and give me your X bar of 5 observations. And I'll plot that. And when I do, the distribution looks like this. Now, it's smoothing out. It's becoming a bell. It's getting longer. The people who drew these pictures try to make the area stay the same, so the bell is getting taller. But one thing I want you to notice is that there's no chance at all of being anywhere near 1 or near 5. There's no way. There's no observation. None of you, no group of 5 came to me, and each of you had numbers near 1. Somebody's going to get a high number, and the average is going to move up. The averages were all getting closer to 3. 3, by the way, is the center of the distribution, the mean of this distribution. The expectation of this distribution is 3. And they seem to be pulling in from the sides towards 3. And at the same time, they seem to be becoming bell-shaped, but tall, skinny bell. Well, okay, 30 of you get together, whole class fulls, 30 people get together. Now I've shrunk this so it can fit on the page. It's a very skinny distribution. All the area is concentrated real close to the expectation of 3. See, there's really no chance of getting anything between 1 and 2 or between 4 and 5. All the data is between 2 and 4, and most of it's concentrated pretty close to 3. Okay? Now these are 30 observations in the average X bar, in the average. Okay, we started out with a distribution that was uniform. Let's start out with one that's pretty heavy near the tails. It's much more likely to get numbers between near 1 or near 5. Not at all likely. In fact, you can't get any number at 3, but just a little possibility of getting numbers near 3. But very likely to get numbers close to 1, close to 5. Very likely. Okay, you each take data, you come to me one at a time, plot your data, and you actually find that the picture looks like that with an infinite amount of data. Well, what will happen if 2 of you came together and gave me an X bar based on 2 observations each? So 2 people get together, give me observations. What happens? Picture looks like that. Wow, what's going on? Well, there's a possibility that 2 people got numbers near 1, so there's still some possibility here. There's a possibility people got numbers near 5, so there's a possibility here. And it gets sort of fun. But look, there was nothing in the middle. Now there's a lot of probability in the middle. And that's because it's very likely someone gets a low number and someone gets a high number. When you average them up, you get a number in the middle. Someone gets a number here, someone gets a number there. The average is in the middle. Someone gets a number here, the average is in the middle. So the middle values are much more likely than they were before, and in fact more likely than anything. And that's only 2. Now 5 of you get together and bring me the average of just all 5. It looks like this. It's beginning to, it hasn't started pulling in from the ends yet because there were still heavy tails, but it looks like the data is becoming bell-shaped. Let me go all the way to 30. 30 of you get together and bring me your sums, the average of your 30. And again, I've shrunk it. Now you see there's no chance of being between 1 and 2 or 4 and 5. All the data is between 2 and 4. That is, the averages are all between 2 and 4, and they're bell-shaped. Bell, this typical bell shape, but it's a very skinny bell. If you change the scale of the diagram, it would be more like that. That's the usual way you see it, but then if you did that, the area would be less than it was, and they were trying to keep the area under the curve the same, so they had to make it very skinny. All right, let's start off with something quite different. Here the mean is around 1. It goes from 0 to 1. It's very heavy near 0. There's really no chance of being near 4. 1, 2, 3. This is 4. There's no chance of being out there at 4. And all the possibility is really close to 0 with an average or expectation of 1. Well, if you all got data from this distribution and came and plotted it, it would actually follow this distribution. But if you came to me in pairs, the distribution would look like that. We plot the data from pairs of X bar, I get X bar from each pair, and there's still chance of being near 0, but there's the center of this thing starts moving up, moving over towards 1, and it comes in from the end. No longer can you get 4. The worst you can do is like 3.5 with only 2 observations. There's really very little chance, negligible chance of getting number out there. With 5 observations, you can see what's happening. It's beginning to pull in. It's certainly pulling in from this end. It's beginning to pull in from that end. And it's again beginning to form this bell shape. That's 5. Let's go to 30. By the time you get to 30, it's centered around its expectation or its mean. It's skinny about it. There's no probability of being out here. And it's bell-shaped, just like all the others were. Well, let me start with a bell shape. This is a normal distribution. This population is called normal. It's a bell shape. The normal curve is a bell-shaped curve, sort of looks like that, depending on how skinny you draw the axes, but generally it looks like that. Now, if you were to get some data from that and plot it, it would look just like that. The normal, the usual, this is the usual form for data. When you go out and get data, this is the expectation. When you go out and get data, you get some value. Most values will be here, some values in the tail, but very little far away. And by the time you get this far away, there's no more data. And so most of the data is right here, near the expectation. That's the way data generally looks when you have a lot of data. Hey, let's take 2. 2 you get together, give me the average. Well, now look, it's still bell-shaped, but it's in from the ends. 3 is the center. what's going on here? Let me see. This was, okay, it started at 1, 2, 3, 4, 5. Okay, it started at 1 and went to 5. It's moved in just a hair from here. Just you can't even see with 2 that it's moved in, but it's still a bell-shaped, and let's go to 5. By 5, it's moved in quite a bit from the ends. No longer at 1, no longer at 5. You're centered around 3, and you're still this characteristic bell shape. Let's go to 30. At 30, looks like all the others did at 30. It's centered around its expectation. There's no chance of being here. There's no chance of being here, and it's bell. And if you shrink this down to the right axes, it will look exactly like it looked in the beginning. The picture of this and the picture that we started with, the normal distribution, are exactly the same except for the scale. So what I'm saying is that if I were to change the scale on this picture here and redraw it, it would look exactly like that. They are both normal distributions, no difference between them. But this is the distribution that we got when we had 30 observations from any other distribution. They all look like that. They all look exactly alike. Interesting. They're also shrinking up towards the expectation so that there's not much chance of being far from your expectation. The chance is zeroing in. And actually, if you did this on and on and on, the picture would get even skinnier, and it would be so tiny you really could hardly see the bell, and it would be zeroed around the expectation or the mean. And the chances of being far from the mean, or any distance you like, small as you like, from the mean, would be negligibly small. Okay, so what does that tell us? What's going on here? What that tells us is the central limit theorem. Let's define the central limit theorem so that we have no problem. Central limit theorem is, and it's a theorem. Well, don't worry about it. Just remember central limit and central, or theorem if you like, has to do with the distribution. Well, let's write it out, and then I'll tell you how to remember it. Central limit theorem. No matter what the individual probability structure looks like, the average tends to be normal. The word tends mean as the number of observations, n, gets bigger and bigger, goes to infinity. That is, we saw 2 observations, it was slightly bell. When we had 5 observations, it was more bell. By the time we had 30 observations, it was really bell. If you have 1,000 observations, it's going to be extremely skinny and very belled. The distribution is normal, meaning bell-shaped. Theorem relates to distribution. And that distribution is normal. Okay? So the central limit theorem says that no matter what the distribution looks like, you're going to end up with this bell-shaped normal curve. So theorem says the limiting distribution is normal, is bell-shaped, and it looks like that if you scale it properly. Okay? Central limit theorem, the shape of the distribution is normal. Okay, the other aspect of this pair is the law of large numbers. In the law of large numbers, the number of observations, let's do it slowly. The law of large numbers. As the number of observations and the average increases, well, same thing we had to do for the central limit theorem, but as the number of observations and the average increases, so instead of 2, we're averaging 5, we're averaging 10, we're averaging 30, we're averaging 100, we're averaging 1,000, averaging 1,000,000. As you go up in the number of observations in your average, all the probability gets concentrated closer and closer to the expectation. And that's what we saw. This curve was getting skinnier and skinnier around the expectation. So there's not much chance of being far from your expected value. That's what makes Las Vegas so profitable. The more people who come into the casino, the more the casino can count on earning whatever the expectation is for each and every person and each and every play. That is, if each person has an expectation of -1 cent, that is, for the gambling casino, it's 1 cent per play of game. Every time someone plays the game, they're going to win a penny on the average. And if they have 1,000,000 people play, or 1,000,000 plays of the game, if they play 1,000,000 times, then they will make that much money one, that's what? It's $10,000. They will make $10,000 on those million plays with not much variation. Maybe it'll be a 10,010 or 9,990, but the expectation will be achieved. That is the expectation, the chances of the average amount, not being the expectation, not being a penny per play, is very small. Might be a penny in a fraction, it might be a little tiny bit less than a penny, but it's going to be approximately a penny for each play of the game. The average is going to be a penny if I have a lot of people in my average. So the law of large numbers says that you might as well consider the expectation as what's going to happen, because that's what's going to happen on the average in the long run. Now what I usually do is play a little game, and I give people a die and let them roll it 10 times, say, and find the expectation. The expectation is 3.5 on one roll of the die. What I do is let them roll it and tell me how many times they got a 1 and how many times a 2. And we go around the room and we see that how many 1s were rolled and how many 2s were rolled and how many 3s were rolled. And it turns out that it's uniform, that the number of 1s and 2s and 3s and 4s is approximately the same. It might be a little bit bigger. So let me draw a picture. Let me go like that. It'll be approximately the same from maybe something like this, all right? Something like that we'll get, or maybe even between if we take them whole numbers. But it's essentially a straight line for that. Then when we want to see what is the average, take an average of those rolls and give me the average. How many are between 1 and 2, 2 and 3, and so on, or this is 1.5, below 1.5, above 1.5, but below 2.5, above 2.5, above 3, but below 3. What we get is a picture that looks more like this. Showing us that the average of the data looks like that when the data looked pretty straight. So when you plot the data, when you actually do this, you plot the data, it's almost a straight line, a little plus or minus. But when you plot the averages of 10 instead of the data from 10, you get a nice picture. And if you did that yourself, you would find that that's what would happen. Okay? So how does this affect us? Actually, the law of large numbers. Law. Oh, I forgot to tell you. How do you know law? Law has to do with expectation. The law of large numbers has to do with the expectation or the average. Central limit theorem has to do with the distribution, the fact that it looks normal. They're two aspects of the same thing. Both cases, they're working with averages. One is the distribution of the average, and the other one is the spread around the average. The spread is very close to the mean. So really, if you get a million observations, you're going to be very close to the expectation or the mean. And if you gamble frequently, you can be pretty sure that how much you'll win total will be approximately your expectation multiplied by how many times you played. The law of large numbers will sort of guarantee that. And so if you're going to gamble, if the stakes are negative and you're going to lose a penny a play or whatever a play, it really doesn't make sense to play small amounts. You'll play a long time, you may be happy, you maybe say, hey, I got $5, let me play a penny, I can play 500 times for that penny, I'll be very happy. Yeah, okay, that's different. If you're playing to win or lose, and you go out there and you play small bets and play often, you're going to end up losing because the expectation times how many times you played will be your long-run average, which will mean your total will be negative. On the other hand, if you go there and you put all your money down on one roll of the dice, one turn of the card, one something, you have a small chance of winning. If the odds on the game were 20 to 1 against you, you have at least a 1/21th chance of winning. You can win. There's a possibility you'll win. If you play small amounts, the law of large numbers will take hold, and there's no chance of your winning, or extremely small chance. So if you're going to gamble and want to win, and the odds are against you, that is, the expectation is negative, bet all your money at once. If your expectation is positive, which I I can't imagine a game where that would be, but if your expectation is positive, play often in small amounts. And in the long run, the expectation will be your average, and then you'll be ahead of the game. Okay? Good luck.